Welcome to the deep dive. Today we're looking into something really fascinating at the forefront of large language models, LLMs.
That's right.
We've all seen how impressive they've become, particularly with tasks like math or coding. They show this amazing reasoning ability.
hmm And a key part of that is how they generate these detailed step-by-step solutions, the reasoning traces.
Exactly, these traces, it turns out they're not just the answer, they show the how. And that how is incredibly valuable.
Immensely valuable. Because that step-by-step process is perfect fuel for something called model distillation.
Right, where smaller models can essentially learn from these traces produced by the bigger, more powerful teacher models.
Precisely. They can study these roadmaps and inherit some of that advanced reasoning capability, but, much more cheaply.
Okay, so let's dig into why that's such a big deal. These top-tier frontier models, they're basically creating this super valuable data set just by doing their work.
Yeah, a data set of their own thought process.
And if smaller outfits can just take that data and use distillation to copy those abilities, well, that's a serious intellectual property headache for the original creators, isn't it?
It absolutely is. Think about the huge investment needed to build these frontier models. If competitors can replicate the key capabilities for a fraction of the cost.
That undermines the whole incentive structure. Why spend billions if someone else can get close for much less?
Exactly. And it might even push these companies towards restricting access, locking down their models to stop this kind of data harvesting.
Which limits the benefit for everyone. Plus, there's a safety angle too, right? These distilled models might not pick up the safety features.
That's a major concern. Safety alignment is complex. Just distilling the reasoning doesn't guarantee you distill the safeguards built around it.
So, amazing reasoning progress, but the byproduct is this easily copied, potentially less safe knowledge. Which brings us neatly to today's focus, anti-distillation sampling.
A potential solution emerging from academia.
Yeah, a novel approach. We want to really unpack the clever bits, the innovative side of how this technique tries to protect these big models. How does it make those valuable reasoning traces, well, less valuable for distillation?
So the core idea, especially from an academic viewpoint, is quite elegant, I think. Instead of just letting the model generate its trace normally,
Uh-huh.
anti-distillation sampling makes the teacher model actively tweak how it picks the next word, the next token, during generation.
Actively tweak it. How?
It subtly changes the probabilities. Think of it like choosing words that still lead to the right answer, but maybe take a slightly less obvious or direct path. The goal is to poison the trace for distillation purposes.
Okay, poison sounds bad, but you don't mean making the answer wrong for the user, right? The original still needs to work well.
Absolutely not. That's critical. It's not about degrading the model's usefulness. It's about making the reasoning path itself less instructive, less easy for a student model to learn directly from.
Got it. So, maintaining usefulness while reducing distillability.
Precisely. The researchers call these the two main goals, or desiderata. First, non-distillability. A student model trained on these altered traces should perform worse.
Makes sense.
Second, nominal utility. The original teacher model must keep its high performance on the task. The balancing act.
A tricky one. So how do they actually manage that? How do you make a reasoning path less instructive without just making it confusing or wrong?
Well, this is where they introduce a proxy student model.
A proxy, like a stand-in.
Exactly, because the frontier model owner doesn't know what specific model a competitor might use for distillation.
Right. Could be anything.
They use a proxy, a representative model, to estimate how useful a particular step, a particular token, would likely be for any student trying to learn.
Okay, so you have this proxy learner. How do you measure if a token is good or bad for distillation using this proxy?
They use something called a downstream loss function. This function basically measures how well the proxy model is doing on the task they want to protect, say, math problems.
Lower loss means the proxy is doing better.
Correct. Typically, they might use something like the negative log likelihood on a standard reasoning benchmark. A lower value means the proxy is learning effectively from the trace it's seeing.
Okay, proxy model, downstream loss. Now, what's the actual trick? What's the core innovation of anti-distillation sampling?
The real innovation is adding a penalty term to the teacher model's process for choosing the next token.
A penalty.
Yes, a penalty, often denoted as delta. This penalty is specifically designed to reduce the probability of choosing tokens that the proxy model suggests would help it learn tokens that would lower its downstream loss.
Ah, so it actively avoids the good teaching tokens.
Exactly, and conversely, it slightly increases the probability of choosing tokens that are predicted to worsen the proxy student's performance. To increase its loss, it steers the generation away from being optimally instructive.
It's like deliberately not giving the clearest possible explanation, maybe using synonyms or phrasing that still works but isn't the most straightforward way to teach it.
That's a pretty good analogy, but there's a big computational challenge here.
Oh.
Calculating this penalty properly, figuring out the impact of every possible next token on the proxy model's loss. That would be incredibly slow and expensive at every single step of generation.
Yeah, I can see that. You'd have to run simulations for every word choice. That sounds impossible in real time.
It would be computationally prohibitive. So this is where the next key innovation comes in, the efficient finite difference approximation.
Okay, sounds technical. How does that help?
Instead of doing that full complex calculation for every token, they use a clever shortcut. They basically estimate the impact.
How?
They run the proxy model forward twice, once normally and once with its internal parameters slightly nudged in the direction indicated by the gradient of that downstream loss.
Okay.
By comparing the outputs of these two slightly different runs, they can get a very efficient approximation, they call it white hat, of how much each potential next token would likely help or hinder the proxy's learning.
So it's a smart approximation instead of a full calculation. Two quick runs to estimate the effect rather than thousands.
Precisely. It makes the whole process feasible. It's a really significant methodological contribution, actually. For listeners interested in the details, equation 11 in the paper lays out the math for this approximation.
Clever, so they can efficiently penalize the good teaching tokens and favor the less good ones. Now, I saw mention of a parameter lambda. What does that do?
Ah, yes, Lambda. That's basically the control knob. It's a hyperparameter that lets the model owner decide how strongly to apply this anti-distillation penalty.
So you can tune the trade-off.
Exactly. A higher lambda means stronger protection. The penalty is larger, making the traces potentially much harder to distill from. But push it too high, and you might start to see a small decrease in the teacher model's own performance.
Right, so it's a balance. More protection might cost a tiny bit of the original model's sharpness. Less protection keeps the original model pristine, but makes distillation easier.
That's the trade-off you manage with lambda. And the researchers, of course, tested all this.
Empirically, what did they find?
They ran experiments using different models for the teacher, proxy, and student roles, specifically mentioning models like DeepSeek, Qwen, and Llama on standard math and reasoning benchmarks like GSM-8K and math.
Using different architectures is important, right? Shows it might work generally.
Very important. And the results were quite striking. Their plots, like figure 1 in the paper, show it clearly.
What do they show?
Basically, for a given level of teacher model accuracy, remember, keeping nominal utility is key. The student models trained on traces generated with anti-distillation sampling perform significantly worse on the math tasks compared to students trained on traces from standard generation methods like temperature sampling.
So it worked. It demonstrably made the traces less useful for the student model.
Yes, it significantly hindered the distillation process, demonstrating that non-distillability goal in practice.
That's pretty compelling evidence.
And as you mentioned, the use of different model families suggests this technique might generalize, it might be effective against various unknown student architectures a competitor might try to use.
Did they compare it to other, maybe simpler methods? Like just adding noise?
They did. They compared it to baselines like standard temperature sampling and also a method called permutation sampling, which introduces noise. Anti-distillation consistently showed a better trade-off. It hindered distillation more effectively for a given level of teacher performance.
So it's not just about making the traces noisy. It's a targeted, intelligent kind of disruption. From an academic standpoint, where does this fit in?
The paper positions it nicely as bridging ideas from data poisoning, where you intentionally corrupt data and techniques for model privacy. It's a novel way to think about protecting the valuable knowledge embedded within these frontier models.
Protecting the IP without just locking everything down completely.
Potentially, yes. It offers a mechanism that might allow for wider use or access while still safeguarding the core, expensive-to-develop reasoning capabilities.
What could this mean for the AI industry moving forward?
Well, if it proves robust and scalable, it could really influence the dynamics. Companies might feel more comfortable deploying powerful models if they have some technical defense against cheap replication. It could impact strategy around open versus closed models.
Interesting. Okay, let's try to wrap this up. The core innovation here in anti-distillation sampling seems to be what
It's that strategic, targeted modification of how the LLM generates its reasoning trace, using that penalty term.
which is calculated efficiently using the proxy model and the finite difference approximation.
Right. To specifically make the trace less useful for distillation by another model, and this is crucial, keeping the original model working well.
And it's tunable with that lambda parameter, letting developers balance protection and performance. Plus, the initial results look promising for actually working against different kinds of models.
Exactly. The empirical validation is encouraging, suggesting it's not just theoretical.
So as these LLMs get ever more powerful and their reasoning becomes this incredibly valuable asset, it really makes you think, doesn't it? How will techniques like this, these defensive measures, shape how AI is developed, how it's shared, and how companies compete in the future?
It's a critical question. Finding that balance between encouraging innovation and protecting the investments that drive it, that's going to be central to the next phase of AI development.
A fascinating area to watch. Thanks for walking us through that complex topic, and thank you for joining us on the deep dive.